Hello, this is the second installment of our series in Mastering Software Engineering and specifically Mastering the Agile Software Development process. Now, last session we talked about the product owner, and today we'll focus on actual software development. Let's get straight into it. Here are our user stories, which we talked about last time. I hope you had the opportunity, or at least you made the effort to implement this application in different ways. At least you started doing so and you faced some of the possible issues. I've explained what those issues could be, and today we'll see how to start an application, start the development in a good way that leads you straight into a successful product, or at least a successful implementation. Now, here we have test first. Okay, you always start with the functional tests. And I say this because, as I explained before, if you start from the bottom up, you do not have a clear separation between translating representation language and translating or breaking down the domain language. Um, Good acceptance criteria, or at least good reading of acceptance criteria, translate them directly into use cases or test cases or test scenarios. Now, I am writing a Java application. Java is my language of choice, but you can use your own language of choice to do this. You will, of course, have to be able to read Java as I explain it, but you don't necessarily have to write it. All of the code that you will see here today was written manually. There is no GenAI involved, at least at this point. We will introduce that later. Also, because this is an educational tool, the test coverage is not 100%. I haven't even measured it. When we go to GenAI, we will also improve that because our ability to write code in quantity will be improved a lot. Right now, we are limited in quantity, but we're focusing on quality. All right, so on our user stories, we start from the first. Right? Get a stack of tiles. Uh, in this one, we have here, for convenience, test method order per annotation. So we're going to execute test cases as if this were a game. Um, we are here creating a preset deck because if we were to here, if we were to write this application as a full game or write this test scenario as a full game, uh, you have a tile has 72, a tile stack has 72 tiles, minus one for the starting tile, and you actually have 71 to be drawn. That's a full game. If you divide that by 3 players, you have 23 rounds. That's a long test, and instead of playing manually 23 rounds in my test class, I am going to, or I have created a preset deck with 6 tiles plus the initial tile. That's 2 rounds. It's a much shorter test class. Now, I have picked specific types of tiles so that I can run this game neatly, testing most features. All right, for this test class, we have the actual game and 3 players. Oops. And we first make sure that we can start a real game. Now this is part of the second test, sorry, the second story. But this is actually the first story, right? We have 24 tile templates. Now, this is the first part where test coverage is lacking, because instead of creating 24 test scenarios or 24 test assertions, I'm just working through those tile designs, or as I call them in code, tile templates, as I write the tests. So for this one, I'm using 7 different tile designs. Actually 6, because this one repeats. Okay, so what does a tile template look like? Well, we have, if we collapse, actually this was collapsed. I cannot collapse this call. Okay, we have 24 tile templates here, and these match this table. So you can see that correspondence between the acceptance criteria and the actual code. If I were writing a tile template test, that's exactly what I was going to do. I just have to pick each tile and verify that its design, as you remember from that image in Paintbrush here, but this design matches what we see on this screen. All right. So these are the tile designs, and we are filling these into that template. Sorry, not the template. That division of the tile into areas. And we just define, so CRFR, we define the city and road parts, and then fill the rest with field. All right, what does this look like? What does a tile look like? These are tile parts, right? So let's open this here. Oh, this is big. So this is an enumeration of 25 tile parts, and I've named the tiles according to their layer. So let's go back to Paint here. So we have a center, and then we have an inner layer, which are these 8 parts of the tile, and then we have an outer layer, which are these ones facing outward of the tile, these 9 parts, and then we have gaps between these outer layers, which are these 4. And then they're oriented according to the geographical directions, north, south, east, and west, ordered in, well, they're not actually ordered because it's very hard to do that, but more or less ordered in clockwise direction. Now that looks like this. Okay, so we have a center, we have inner north, this inner north neighbors the center, inner northeast, inner northwest, and outer north. What does that look like here? So this is, let's take this yellow here. So this is the tile that we're looking at, the inner north. And so it borders, let's do it in blue, it borders outer north, inner northwest, inner northeast, sorry, the opposite, right, and center. So whatever feature we find here will expand to these directions. We also do another thing when we rotate this tile, and this was added later, so when we rotate it, the feature in it goes to inner east. All right, so these are tile parts, but we didn't add this at this point, right? We're just saying that these parts exist, and this is the feature in each of those parts. So when we look at the tile, we have a map of parts, saying what's the tile part and what's the feature type in that tile. Feature type again is an enumeration of the features. Abbott City, Field, Road, and Village, which are all the parts that can be in a tile. Right? City, field, road, village, and the Abbott here. We'll talk about the parameters later. All right, so once I have this deck, I can actually do something, start a game. Back to our story here. On a standard deck, each tile template has a definite number of instances. So if I would have to do this, let's Cert does not throw. Okay, let's this deck assert the deck size is equal to 72. And a shuffled deck always has the initial tile at its top. Right? That was initially here. It was moved to the constructor of game once we implemented the other stories. All right, so that's the first story implemented. Here, what I could do, what the code initially read, this. Step, iterating next. That. Parts is equal to template crfr build get parts. Right, so this was the initial reading. We want to make sure that the tile at the top of the deck is CRFR. And this is also checked in Avila Game, the constructor. But that's the story implemented, period. When we have this test and some others for coverage done, we're done with the story. We can move to the next. All right, so tiles can be placed on the board grid. Here's where things start to get interesting. So as a player, I want to draw a tile from a single deck of tiles. The game starts with n players. Right? We have here a game that needs a tile. Okay, so it starts with 3 players. Player count here. And we created players here. Now, why is this a supplier? Or actually a by function. Why is this a function and not just being called in here? Might as well be. But initially, I wanted to create a player that plays automatically so you can play against the computer. But I walked that back. So it just creates a player in the game. And then, okay, the game starts. The tile on top of the deck is placed on the center of the grid. There should be, if we're translating this directly into tests, there should be an assertion here that board grid tile at the origin of the board grid, so the center. So how do we know that this is the initial tile? We would have to get the reset deck. Right, so the tile at the origin of the board is the initial tile, which is CRFR. We know that CRFR because of the previous test. All right. So that's just translating the acceptance criteria. Game starts, tile on tile. So that's it. This is acceptance criterion 1. Acceptance criterion 2 after the game starts. So this is after the game starts. Well, player 1 can draw a tile. So we have player 1 is the current player, and player 1 draws a tile. Then places it next to the initial tile. This doesn't say which direction, so we have to create or invent those specific details. And we're placing that tile, which is a CFRR, on the east from the center of the board. Now, origin here, just in Cartesian terms, is the center. And we're putting that tile east from that center. And then we make sure that the tile at the x-axis +1 from the center, and y is the tile that we just drew using player 1. All right, we will have these, we'll talk about these in a minute, but that's acceptance criterion number 2. And then 3, after placing the drawn tile, player 1 can end its turn. Here it is, end round of the game. Now player 1 cannot draw a tile, and player 2 can draw a tile. We see here the current player is not player 1, so player 1 cannot draw a tile. We could just ensure here another thing, assert throws. I think we can just have this. Player 1, draw a tile. Nope, we can't. Right? This would make it. This would make a exact translation of the acceptance criteria. Oh, actually, it's right here. It's right here. And then we also have the second round here is a different test scenario where player 2 draws a tile in that same game. Right? Okay. Actually, there's something here important. I realized that there is one acceptance criterion that is not explicit here. And that's one of the questions that might come up when the product owner is refining that story, explaining that story to the software development team or the software engineers, is that, okay, can I end that round? It's not a round, it's a turn. Let's rename this end turn. Right. Can we end the turn before we draw a tile from the stack? as far as I can tell from the game rules, that's no. So there we go. One part or one variation of the acceptance criterion regarding that specific aspect of the game. All right. So now we have our test. We know what needs to be done to get the acceptance criterion fulfilled. And so all we have to do now, we translated the representation language from English to programming language, to Java. And now we have to break down these concepts because as you write the tests, none of that is implemented. So you know that a game, for instance, has a current player, and you know that the current player changes after you end the turn. And you need to do that as all of that, creating the deck, the players, as in the context of a game. So we create the game, we have a tile stack, we add it here, we create the players, and we start the game. Okay, now one more layer of abstraction. What does it mean to start the game? It means, okay, we get the first tile of the tile stack, which must be that CRFR. You get a board grid. Now, what does it mean to get a board grid? If there is no board on that tile, meaning this is the initial tile, you create this board grid. Now this is an implementation choice. I could have created the board grid outside this method and then assigned it to the tile. Those are implementation choices. All right, so we create that virtual grid where we place tiles, and we place the tile, set the location of the tile to the origin. Quite interesting. What happens, and then you set the current player to the first player that you created. What happens when you set locations? It's just a property. Now here's one interesting thing. When you create a grid, you have to create it using an initial tile, and then you place that tile on the origin. Oof. Okay, what does it mean to place a tile at a certain location? To place that tile at a certain location, you need an array of tiles with 2 dimensions. Right, so this is created as a Cartesian grid, and it has a certain grid size. Right, I've created this grid size with 1,000 slots from one edge to the other. We have 72 tiles, so a grid size of 144 would be sufficient for the game, right, for all scenarios, because with 72 tiles, you can line them up in one direction because your origin must be the middle of the Cartesian grid, because you cannot have negative array positions, right? So you organize it like that, and you have a sufficiently large grid. Could you make the grid size dynamic according to the depth of the tile stack? Yes. Could you have made it in a different way, like a dynamic map instead of a tile grid? You could. Those are all design or implementation decisions made at this level, at this domain. So this doesn't pertain to how you play the game, but rather how you assemble its parts. All right, so to place that tile, you set the location in the tile, you set the board of the tile grid in the tile, and set the tile location. I notice now that there is here. This is actually, place the tile, get board grid, starting that. See, this is actually duplicated, so we can remove this. So imagine building this from the bottom up. You first create the board grid, you say how you're going to place a tile, and then what is a tile? We have to work through this definition. You have to walk through all of these different levels of abstraction, and you have to keep track of all of them, or how you're going to build all of them in the future before you have any vision of that. With this approach, all you have to do is, okay, I have no idea where I am, execute the tests, and you know where you are. You know what you did wrong, and you know what you have to complete. All right, so we're back to game test here. So that creates a game. Once I create the game, I have to get the current player. Right, this is just a property that we're setting at the beginning of the game. So if I didn't have this, and I say, okay, I created the board grid. What do I have to do next? The test will fail. Here it's saying, oh, you have to tell me what the current player is. The current player draws a tile, and that's very simple. We just get the next tile from the stack. And then you put that tile on some location from another one. So this is an easy way for me as a programmer to reference some location. I can just say, okay, given all of the directions in a tile, I can just get a reference point and get the point from that reference point. Easy peasy. And as you can see, I'm referencing the locations using point, which is an existing class, Java AWT point, that just contains Cartesian disposition, right, in 2 axes. All right. So when we put that tile, we have the rules here for placing a tile. Right? It can only be placed next to a tile already on the board. The tile cannot be placed at a location on the grid where another tile already is, and the features must match. So when we do this, we say, I will prevent moving this tile, meaning once placed, the tile cannot be moved. I will prevent a replacement at that location. So that's this. And I will check all of the connecting sides of this tile at this location. And if nothing fails here, I will place the tile. I know how to do this already. So this abstraction is already defined at this point. I translated my acceptance criteria into code. And now I have 3 abstractions that have no meaning in my engineering. So prevent moving is, okay, if this tile has a location, meaning it's already on the board grid, we throw an exception. This abstraction is, okay, I don't want to move the tile. Oh, sorry, I cannot replace a tile at this location. So if there is a tile already at the location indicated here, so no replacement. And I check the connecting sides. Now this goes back to our definition of a tile. I'm just determining here if there is nothing around this location, which is here. It must be placed on a tile or next to a tile already on the board. So if there is nothing around that location, we say you cannot do that. And now do we determine if there is something around this location? We just go over all of the directions. And remember, we have 4 directions: north, east, south, and west. We get the direction from that location, so east. So north from that location, east from that location, south from that location, and west from that location. We get another tile that's there. If there is no other tile at that direction, just move to the next. If there is a tile on that direction, we say, okay, now there isn't nothing around the location where I want to place the tile, and I check if the tile matches the other tile on that direction. Now again, new abstraction, check match. Now at this point I said, okay, if I want to test in this particular test case, I'm looking at CRFR here. I'm looking at a road, field. So if I go to my drawing, it's a similar thing as this, except we have fields here. So CRFR, and then I'm connecting a CFRR. So CFRR, we have road here, city here, and field on the rest, right? Okay, we're checking if these connect, meaning I want to check if these connect. I'm going yellow here, thicker. I want to see if these connect. And then these and these. Right? If all 3 connect here, I can place this tile next to this tile on this direction. But also I have all of these different types of tile borders, right? We could have something here connecting cities. We could have something here connecting fields. We could have, what else? Yeah, that's it. So I need at least 3 test cases to make sure that this check what? Here, check match actually works. So I went to tile test and create a new test saying, okay, what should happen if 2 tiles, one next to another, mismatch? And then I have the field match, the road match, and the city match. These are the 3 types of connections or between tiles. And we're using exactly that method. So I have one tile here, which is CRFR, and here I have only fields, and I want to see if the first tile at the north matches the next tile. So first tile at the north, does this match the next tile, which must be on the south, which is city versus field. So this must mismatch. This one is CRFR again, since CRFR has all of the possible borders. Once again, I'm matching field on all sides, but now I'm matching on the south. This should work. Now I can just say here, assert, no, throw. Oops, search does not throw. Just to be specific about what I'm testing. I'm testing that this call does not fail. Likewise, checking against a road. So road on the east of the CRFR. And city on the north of the CRFR. I could make it more clear by doing this. Right, I could inline the first tile variable and just say I want to make sure that the CRFR at the north matches the CCRR when I rotate it twice. So this is actually also testing the rotation. The rotation here is always clockwise. So rotation here, for the rotation we have to also introduce more things. So what happens when you rotate a tile? We briefly mentioned that. All right, so when I implement this, and you will see, check match. So now I can go here, and reading this should be quite simple. Let me just, oops, adjust the division here, or actually close the other tabs, move the stories here to read this. Right, to check if this tile matches another tile on this direction relative to this tile, the current one, we just make sure that every part where the direction of that tile matches the tile direction. Right, so we have this, the feature on this tile. We're basically filtering these three here. Right, whether it's these three on the east, the south, or the west. And we're getting what features they contain as a map, right? So I'll have all three. I won't have just the road, just the city, just the field. I'll have all three. And then I do the same with the other feature. However, feature part, oh yeah. So I'm taking each of these parts and I'm taking the feature on the opposite side of that part. So this feature, let's go this way. So the feature on outer east, the opposite part is outer west. So I get the feature on outer west and match with outer east. If they're the same, I can connect this. Same thing for outer east north and outer west north. Just for clarity, if you didn't read the code yet, I hope you have. This is outer east north and this is outer northeast. Your order matters. What does it mean opposite? Opposite, you just have outer northeast southwest. The opposite of north is south. The opposite of east is west. And you get that other part. Again, implementation is a choice. I could have implemented this another way. So I'm getting by name. And again, if the other feature matches this feature, or it doesn't match, we throw an error. If we complete this method without error, it means all of the feature parts on that direction match between the two tiles. So this abstraction is done. I don't have to remember how it's used. I go back to tile test, and if I've implemented this correctly for all parts, or for all sides, And that's another test, right? I'm checking north, south, east, and north again. This test class doesn't cover west. So again, coverage is important. All right, back to game test. So at the end, we put a tile. Where's the story? Forwards, no tiles can be placed here. So we put the tile. We check that the tile at that position is the tile that was drawn by the player. The acceptance criterion doesn't say anything about followers yet. And we end the turn. What does ending the turn mean? It means forget about scoring. We haven't talked about that yet. Here, if we have an X tile on the stack, we just change the current player, move it to the next one, and the current player no longer has the tile that it has drawn, so we remove that. Once again, only the current player can end the turn can only end when the player has drawn a tile and has played it. So those are not spelled out in the acceptance criteria either. So I can also translate back and say, okay, the acceptance criteria were lacking. And that's it. So I wanted to walk you through those steps of building an application by translating first the representation language from English to Java, and then you have the acceptance criteria as software, as a test scenario, and then you break down those parts into its components. So what are the benefits that I reap with this approach? Number one, I know when to stop. I'm not working infinitely saying, okay, oh, I remember I have to do this also. I can also do that, and so on, until you finish the application when all you needed to do was one small change. Another thing is, at the end of each story, I have an application that is that much closer to being complete, and it's usable. So as a game engine, I could have a game where I only put tiles next to each other, and the tiles match, but nobody scores. So I can run through the end of the game. Is there any fun in not being able to win the game? I don't know, but at least we're that much closer to having that game. Whereas if you write your stories explaining everything that needs to be done at that point, like scoring, then you won't be able to progress or to complete your progress in laying down the tiles until you score the players. Right? So on this one, we can place the followers, so we do the same thing with followers and so on. It would be incorrect for me as a software engineer to go to tile, for instance, and say, okay, check match. What is check match? Or I mean, check match is a part of what? And I go to the test and I say, oh, okay, test match or check match is something that verifies that the tiles can be placed next to each other. Oh, so that's how I place tiles next to each other. I just check if they match and place them at that location on the board. No, you have to actually go to that abstraction, right? So here, I have an usage on the board grid, so this is not a test. This is part of checking the connecting sites. And when I go to the usage, I see that it's part of placing a tile on the game. Right, so this is a top level abstraction, and I do that. Another thing is your domain language should match as close as possible. So when I was at the game test here, I have something that I called on the code tile template. But in my stories, a tile has designs, right? And I called tile template here because a template is something that I use to build or to construct the tile. Whereas here, a design is also a template that I'm using to construct the tiles. So tile design and tile template are the same thing. I should rename one of the two. So I'm going to do that in the story. Right? Design, I'm going to use template. And I actually also use the template here. So this is one job of the product owner, to make sure that our language is not ambiguous, that I'm not using the same term for different purposes, and that I'm not using different terms for the same purpose. I've also added two things to here, our team. Now, the product owner, as I mentioned, you have some qualitative metrics to tell if you have a good product owner, or if your product owner is producing good stuff, good stories. And I've described, I think, each of these, except for maybe the two last ones. We also have the same thing with the development team. So how do you tell if your software engineers produce good software? Number one, as I've demonstrated or shown throughout this session, you can produce pseudocode directly from the code by translating it from programming language to natural language. Or another way to phrase this is, product owner or anyone in the team can ask an engineer to explain how something works in detail, meaning breaking down those concepts or those abstractions. And he will walk the product owner or whoever asked through the code, just like I did, one level of abstraction at a time. And that will tell you that the application translates only one type of language at a time. Because I can walk through the code like that because I translated the code from Java to English at that abstraction level. Another point is anyone can make changes on code written by anyone else. What usually happens in projects is you get a story and say, oh, this story is on top of such feature, so we should assign this to the same person that wrote the code. Or you get a bug and you say, oh, the code that this bug is about, or that causes this bug to emerge, was written by this person. So this person is going to fix that bug. What happens if that person left the team? Do you bring that person back to the team just to fix that piece of code? Do you need time or more time to analyze the bug and determine the cause, or can you just read the code and read the error and determine the cause and the solution? And finally, the assignee of a story, ideally everyone in the team, knows how to test it before starting to write the code. So if we go back to our stories and I go to the next story, here, players score points during the game for completed features. As a player, I score points when a feature is completed, and features are considered complete when these things happen according to the feature. I'm not sure why something crashed here. Yeah, I cannot select text anymore. So fields and villages are never completed, so you don't score points during the game. Roads are completed when every tile in the area, every tile area in the feature has a neighboring tile area that is a different feature. Oof, this is a long text. And then you award 1 point per tile. Cities are completed with the same condition as the road. And then the abbot needs all surrounding 8 grid locations, so the immediate neighbors and the diagonals, to be in the board. And you award 1 point per tile. So remember the 3 parts of the story. So you need a good product owner. So you have the background, which is the state the application is in before the action happens. And the state here is at the end of each round. So the round, again, terminology, right? It's not a round, it's a turn. Every feature on the tile placed by the current player is checked for completion. So when I put down, let's say it's this tile. Let's say I place this tile. Where's my square? Here. So now I check each feature of this tile. This tile has 4 features. A city here on the north, a field on the north and east, a road that crosses the tile in 2 directions, and another field here. Now I check that each of these features is completed, and if any is, I award points. How do I know that this feature is completed? I use this criterion, which is, let's take the road for instance. We take one random area of the tile, let's say the center, and we start expanding. So this tile is our neighbors, all of these 4. This one is a road, this one is a road, this one is a road. I get to this end and I say, okay, this has 1, 2, 3, 4 neighbors. So this is the 4th. And I see one empty area here because there is no tile on this side. So this feature is not complete. And this is not visual. As I mentioned in the previous session, these are all descriptions that I'm doing with the visual assistants, but they're all textual. And then if I had a village or a city at the end of the road on either side or on both sides, the road would be completely surrounded, and then I could award the points, right? So I have the variations here. I would need at least 4 or 5 test cases to determine each feature type being completed and incomplete. So now I have 8 test cases. And then I have players, only players with the maximum number of followers in the feature are awarded points. So if we want to be feature complete in our coverage, I would have competition for these 3. So 8 plus 3, that's 11 test cases. So we could have a single follower, multiple followers by different players competing, and then only 1 player is awarded, and then 2 players are awarded. So 3, 6, 9, 10, 13 test cases, and all followers in the feature are made available to the original players. So that's 1 for each of these. 13, 16. We should derive around 16 test cases for this acceptance criterion only. That's what a good software engineer should be able to do. And then we made this, and the historian knows how to test it before started writing the code. Right? It knows how to test before writing the code if you can derive all of those test scenarios from the acceptance criteria. So from one acceptance criteria, if I want it to be feature complete or complete coverage on that feature, I would have to create 16 test cases, more or less. I didn't write anything down, I did all of it in my head, but it would take that time to do that. And what are the skills of a software developer? You need to be able to, and these skills overlap between the roles, QA, architect, I don't know, designer for any specific part of the application, DevOps. So you need to have abstract thought and domain language identification. These are not skills that are taught in university if you're doing computer science or something like that. You need to be able to understand abstraction layers and when they create a different domain. Remember last time I talked about commuting to work and how commuting, driving, and burning gasoline are different domains, or auto engineering? This is what a software engineer must be able to do too. He must be able to translate between natural language and programming language. Remember how I was explaining how the code works, and I would just explain things in English rather than Java? That's a software engineering skill. Again, we're not taught translation skills in computer science. You can have, for this skill, purpose-specific knowledge of the programming language. I remember one company used TTCN, which was a testing platform specific for certain purposes, and they used it for SS7 testing, which is a protocol for real-time phone calls, unlike IP calls. They used it for IP as well. So you could have Java, JavaScript, Gherkin, or Cucumber, and you're a good software engineer in that area. You also need knowledge of tools that are purpose specific and how they translate to usage in natural language. One small example of this is the usage of the point class. I know that AWT, which is the first framework for creating UIs in Java, writes things in a Cartesian plane. And I know that the way to reference that Cartesian plane is a point. And I was using a Cartesian plane for this application, so I used a point. A very, very simple example. But you have another here, like queues for asynchronous processing, APIs for cross-application calls, Docker, JUnit, Selenium, so on and so on. Right? So this is how you measure, or this is how you select your software engineers, and some other hard skills of software engineering. But this is what they don't teach you in college or university, and you still need these skills to be a good software engineer. Right? Okay. So if you complete your development and if you finish going through our code here, what we have, okay, this is messed up. Let me reopen. Okay, good. At the end, we have the game engine. On our next session, we'll talk about imperativeness. Ooh, we're full of difficult words. In this iteration, we were very little imperative, meaning our acceptance criteria had general terms, because the usage here is very loose. And we're just creating the engine, so there is no actual user or player playing the game. In our next session, we will do two things. Imperativeness. We'll create a user UI. We're actually going to create a functional game using more or less the same user stories, but we'll increase the imperativeness of the stories, and you see a big difference in how they're written. So we'll be able to compare those two, the stories for the game engine and the story for the game UI, and you'll see that there is a complication in how you write stories at your job, how you write stories for leisure applications, and how you write stories for LeetCode. So game challenges or coding challenges, for instance. So that's going to be very interesting. I hope you finish this one on your own, so we're prepared with a game engine on your language of choice, or even if you want just to follow up on this one for our next session. Until then.